In this video, Bayesian classification method will be covered. X be a data tuple. In Bayesian terms, X is considered as evidence. Let H be some hypothesis, such as that data tuple X belongs to a specified class C. For classification problems, we want to determine probability of H given X, the probability that the hypothesis H holds given the evidence or observed data tuple X. Probability of H given X is the posterior probability or posterior probability of H conditioned on X. The attribute age and income respectively, and that X is 35-year-old customer with an income of 40,000 rupees. Hypothesis that our customer will buy a computer, then probability of H given X reflects the probability that the customer X will buy a computer, that we know the customer's age and income. P of H is the prior probability. Probability of H given H is the posterior probability of X conditioned on H. It is the probability that a customer X is 35 years old and earning 40,000 rupees, given that we know the customer will buy a computer. Probability of X is the prior probability of X. Using our example, it is the probability that a person from our set of customers is 35 years old and earning rupees 40,000. Calculating the posterior probability P of H given X, Bayesian classifiers have the minimum error rate in comparison to all other classifiers. Naive-Bayesian classification steps. Naive-Bayesian classifier or simply Bayesian classifier will work as follows. Let dataset D be a training set of tuples and their associated class label, and as usual each tuple is represented by n-dimensional attribute vector x equal to small x1, x2 up to xn, with measurements made on the tuples from n attribute respectively a1, a2 up to an. Suppose that there are m classes C1 to Cm. Given a tuple X, the classifier will predict X belongs to the class having the highest posterior probability conditioned on X. That is, an Bayesian classifier predicts that tuple X belongs to the class Ci if and only if probability of Ci given X greater than probability of Cj given X. For 1s less than or equal to j and less than or equal to m, j is not equal to I. Then we can maximize the probability of Ci given X. The class Ci for which probability of Ci given X is maximized is called the maximum posteriori hypothesis. As P of X is a constant for all classes, only P of X given Ci or P of Ci need to be maximized. In order to reduce the computation in evaluating probability Xj Ci, the naive assumption of class conditional independence is shown on the screen. If Ak is categorical, then P of Xk given Ci is the number of tuples of class Ci in dataset D having the value of Xk for Ak divided by CAD, the number of tuples of class Ci in D. B. If Ak is continuous value, then we need to do a bit more work, but the calculation is pretty straightforward. A continuous valued attribute is typically assumed to have a Gaussian distribution with a mean mu and a standard deviation. It is defined in the equation 6.13 and 6.14. Step number 5. In order to predict the class label X, probability of X given Ci and probability of Ci is evaluated for each class Ci. The classifier predicts that the class label of tuple X is a class Ci if and only if the probability of X given Ci, probability of Ci greater than probability of X given Cj, the probability of Cj for 1 is less than or equal to j, less than or equal to m, j is not equal to a. In other words, the predicted class label is a class Ci for which P of X given Ci, P of Ci is the maximum. Predicting a class label using Bayesian classification, the data tuples are described and by the attributes age, income, student, and the credit rating. The class label attribute buys computer has two different values, namely yes or no. Let C1 correspond to the class buying a computer equals to yes and C2 correspond to buying a computer equals to no. The tuple we wish to classify is X is age equals to youth, income equals to medium, student equals to yes, then credit rating equals to 4. We need to maximize probability of X given Ci, probability of Ci for I equals to 1, 2, P of Ci, the prior probability of each class can be computed based on the training tuples. Contains 14 records. Out of 14 records, 9 records containing S category and 5 records containing no category. Thus, we are going to find out the probability of buying a computer yes equals to 0.643. Buying a computer equals no, and that is 0.357. To compute the probability of X given Ci for two classes, for I equals to 1, 2, we can compute the following conditional probabilities. For all the S categories, for all the no categories, for all the attributes, we can calculate. Likewise, for age equals to youth and buying a computer equals to yes. Age equals to youth and buying a computer equals to no. For all the attributes like income, student, and credit rating also calculated. Using the above probabilities, we can obtain probability of X. X means for the given data tuple, new data tuple, buying a computer X, yes means the values we have arrived 0.222 multiplied by 444 for medium, 222 for youth, and 444 for medium, and 0.667 for student, 0.667 for credit rating. That result is 0.044. Similarly, for the given data tuple X, we are going to compute the buying a computer equals to no. The result is 0.019. To find the class Ci that maximizes the probability of X given Ci, probability of Ci we can compute. Then probability of X buying a computer equals to yes, and probability of buying a computer equals to yes is 0.044 into 0.643 equals to 0.28. Similarly, we can compute for no category also, that is 0.007. Therefore, the Naive Bayesian classifier predicts buying a computer equals to X for the given data tuple X. The given data tuple means the new data is coming. For this, whether he is going to buy the computer or not, as per the Naive Bayesian classifier, he is going to buy the computer. The result is buys computer equal sign yes. Using the Laplacian correction, we can avoid the computing probability value 0 also. The probabilities of these events without Laplacian corrections. And using the Laplacian correction for the three quantities, we pretend that we have one more tuple for each income value pair. The corrected probability estimates are close to their uncorrected counterparts, yet the zero probability value is avoided.